Hey everyone, so today I'll be going over the basics of logistic functions. So what it is if you kind of remember back to biology, we have S-curves and J-curves. J-curves are exponential functions and S-curves are logistic functions. And what they do is they kind of model population growth. What I've did is I've drawn kind of like the graph of a logistic function. So as you can see, it takes on that S shape. So my x-axis I have time, and y-axis I have population, so I'll just label it T and P respectively. So what you'll notice here is that there's an asymptote at 0 and there's an asymptote at L. So what L is your carrying capacity. So this graph will never touch or pass 0, nor will it touch or pass L. Now in the real world we know that population can pass the carrying capacity before it comes like crashing down. But in the math world, it won't ever pass L and it won't pass 0. So if you have a question that's like, when will the population reach L? Well, graph over here, you can see that it will get infinitesimally close to L, but it'll never reach L. So basically as t approaches infinity, that's when it will reach L, but you know that there's not a value on here that it'll reach L. Also, here's a very significant point on the graph is L over 2. And shown by this like kind of red line and this X right here. So what this symbolizes here is this is the inflection point. So right below here, that's concave up, and above the X is concave down. And this tells you like kind of like where the population is increasing the fastest. So here's the steepest slope. Steepest slope is right here. And also like when is the population when it's increasing the fastest? It's just L over 2. So if L was 500, L over 2 is 250. That's just the graph and kind of like the different parts of it. So usually what you're going to do is kind of like you're given a differential equation and you have to find a general solution to it. So the differential equation is dp over dt equals kp and times quantity 1 minus p over L. So going over these variables, your p is just your p values or your y values. L is your carrying capacity, and k is your constant of proportionality, or the book calls it kind of like maximum growth rate if it's a logistic growth function, just like this, or maximum decay rate if it's a logistic decay function, which is just like the opposite of this. And then going from this to a general solution, you have P equals L over 1 plus BE to the power of negative KT. So going from differential to general solution, you just kind of like put your L at the top, and you'll either solve for 1 or 2 of these variables, which is B and K. So you might be given a K, you just plug in K, but it's negative K, so just make sure you put negative K. And then, so we're just gonna do an example of that here. So say if you're given a differential equation that's dp over dt equals 2p 4 minus p over 20, and given like a point 0, 5. So it asks you to find the general solution to it. Well, first you might look at this and you just plug in your K's and your L's. But going back to this kind of like the standard form of a differential equation, you said there should be a 1 here, but there's not a 1 here. So what do? We factor out a 4. So this factor out the 4, we get 8p 1 minus p over 80. So we factor out the 4, and now we can start filling in our general solution. So we have P equals L, which is the carrying capacity. So here's the L, that's 80 over 1 plus B, we don't know B, we're going to solve for B. E to the power of negative K is 8t. So to solve for B, we're going to plug in this point, 0, 5. So this is T and this is P. So we have P is 5 equals 80 over 1 plus B E to the -8, and then t is 0. And then we're just going to solve for b. So simplifying this, we get 5 equals 80 over, and you see here that e is to the -8 times 0, 8 times 0 is 0, e to the power of 0 is just 1, so the bottom is just 1 plus b. Now you can cross multiply, so 5 plus 5b equals 80. Subtract the 5 over, you get 5b equals 75, and divide that by 5, you get b equals 15. b equals 15, and now we're just plugging it back into our equation that we made earlier. So we got p equals 80 over 1 plus 15e to the -8t. So this will be your solution to your differential equation. So what you can do with this solution is, say if it asks you to find what is the population at t equals 5, just plug in your 5 and it'll give you your population, or it'll ask you at what time t is population 500, plug in 500 and then just solve for t. Alright, and that is all you need to know, or most of it, for logistic functions. Thanks for watching.